one. Well done. Lovely. Thank you very much on sound. A good afternoon, everybody. Welcome back. Thank you for coming back. Your time will be well spent, I assure you, this afternoon. If you thought this morning was interesting, this afternoon is even more so. We have an extremely accomplished panel who will deliver some great insights. There are many possible routes to achieving decarbonization, as we know, and many technologies are being tried in laboratories and pilot plants. But can those solutions be scaled up, and how quickly can they be scaled up? And we're going to be hearing now some presentations and then taking some questions on this topic. So I'm going to hand over to somebody with huge expertise. He's a consultant, but don't hold that against him. He still has a lot of expertise. So please welcome Hooman to the stage. Hooman, it's all yours.
Thank you very much, everyone. It's after lunch. I hope you're not tired and you're full of energy for this session. We have extraordinary people in the session, extremely knowledgeable about the topic that we are going to discuss, so hopefully you would enjoy the conversation. If you have any questions, I would encourage you to use the app, how do you call it? And we try to go through them as much as we can. As you all know, CCS could potentially be considered as a very expensive system. As you all know, there are so many research going on across the globe. We are trying to find alternative solutions. Some of them, they only work in lab or small scale. Some of them, they might need investment to grow. So that investment could be from the government, could be from finance, could be from investors, but that is extremely important for all of us to focus on that one and support such new technologies. People that we have in the panel, they are coming from different backgrounds. Some people are coming from startup companies, small companies that they have their own new advanced technology and they would really like to scale it up. Some are representing major industrial companies like energy companies, including Equinor and Saudi Aramco. So we basically have a very wide range of expertise in the panel. We would really like to hear their part of the story in research, development, new technologies, how they are applying it in their own system, in their own organization, and how we can potentially support each other to accelerate the process. That's the only way that we can hopefully reach the net zero target. With no further ado, I would like to introduce the first presenter, Mr. Ahmed Osman. Mr. Ahmed Osman is the Regional Business Development Manager for Equinor in the Middle East. He is responsible for Equinor's commercial and business development activities in the region. He is based in Doha, Qatar, since 2020. Ahmed has 20 years of experience in energy industry and has worked in Egypt, Qatar, USA, and in the UK. So I'm personally interested to know how these countries actually varied from each other, at least in energy transition space. His previous roles included managing the HSE and regulatory affairs team in Egypt, and then afterwards in Alaska. After moving to Houston in 2013, he was a project manager for business development projects in the US, Canada, and Mexico. Before joining Equinor in 2008, Ahmed was heading the HSE department for British Gas in Egypt. Ahmed's core expertise is in sustainability, strategy portfolio analysis, commercial and business development. Ahmed holds a master's degree in chemical engineering from Cairo University and completed different courses in Harvard and Oxford universities related to the topic. Please allow me to welcome Mr. Ahmed for his interesting presentation.
Thanks a lot, Hooman. Ladies and gentlemen, distinguished guests, gives me a lot of pleasure to be here today and to share with you some of Equinor's experience in CCS. Equinor, for those who don't know, is previously known as Statoil. It's the largest oil and gas company in Norway, and we've been in the industry for more than 50 years now. We changed our name in 2019 from Statoil to Equinor to highlight that we are an energy company, not just an oil and gas company. And since then, we've put a new strategy. with the aim to reach net zero by 2050. That strategy is based on 3 pillars. One of them is to optimize our oil and gas portfolio. And CCS plays a big role in that. We're fortunate enough to have one of the lowest emissions for our oil and gas production by less than 6 kilograms per barrel. And that's basically from our CCS projects and from our electrification projects in Norway. The second pillar in our strategy, renewables. We're focusing mainly on offshore wind, and we have targets to reach 15 gigawatts of renewable generation by 2030. And the last pillar for us, what we call the low-carbon solutions, which includes the carbon capture and storage and hydrogen. We're aiming to reach between 15 and 30 million tons of carbon captured by 2030. And to highlight our ambitions here, we have set a target to spend half of our gross investments by 2030 on renewable energy and low-carbon solution, which is more than $5 billion a year. But why is carbon capture and storage important? For us, there are 3 reasons. One, reducing the emissions from our operations. And I will share some examples from our projects in Norway where we captured carbon since the 90s. The second element is to provide CCS as a service. One of the key flagship projects we're working on right now is the Northern Lights, and I will highlight how we're using that for creating an industry for carbon capture. And the last pillar is to use carbon capture as an enabler for blue hydrogen production. Blue hydrogen is the hydrogen produced from natural gas with capturing the carbons through CCS. I know it's very hard to read that slide, but it represents some of the key projects we have right now in our portfolio. You probably can see that most of these projects are either in the US or in Europe. Key reason for that is the incentive mechanisms and subsidies that are provided by the US government and the EU. I'm going to take a few of these projects as examples of what we're working on. I'll talk about some of the existing projects we have, which is the Sleipner and the Snøhvit projects. And again, I will share some light on the upcoming projects, which is the Northern Lights. This is a project we're very proud of. It is the longest serving carbon capture and projects in the industry offshore. Started in the 1990s in Norway, capturing CO2 from the Sleipner field in Norway, injecting it to the Utsira formation. We're capturing around 1 million ton per annum of CO2. And we've done significant amount of studies to make sure that the CO2 is captured properly. We've done 4D seismic, a lot of modeling and simulations. And this project proved that CCS is doable with very limited consequences to the neighboring environment. One thing I want to highlight is that data from this project are available for the public for free. And the idea is to share this knowledge to make sure that this industry can grow. Another example that I want to share is the Snøhvit, which is the first LNG project that utilizes carbon capture and storage in Norway. We've been capturing carbon for around 15 years now, capturing around 700,000 tons per annum. One of the things that made this project viable and commercial is that we are receiving CO2 tax exemptions from the Norwegian government. And again, the message here is that it takes government support for these sort of projects to be materialized. Another project is Ain Salah in Algeria. We started capturing CO2 since 2004. We stopped that project in 2011 because we wanted to make sure that the CO2 is not impacting the neighboring water reservoirs. We're going to restart that project again. We're talking now with the Algerian government. And a message from that slide is that constant studies has to be done for any CCS projects to make sure that the consequences are limited. The final project that I wanted to highlight is the Northern Lights. We're very proud of this project. It's our flagship project in Norway. And the idea is to industrialize CCS. Our role in Equinor here, with our partners Shell and Total, is to help industries decarbonize through collecting their CO2 emissions, shipping it offshore, and store it in the formations in the North Sea. The plan is to store more than 30 million tons when all the phases of projects are completed. It's going to be the largest of its scale. And the good news is that it's not just helping the industries in Norway. There has been agreement signed now with Netherlands, with Germany, to also support some of the industries there in capturing and storing their CO2. With that, I would be very happy to hear your questions, and thank you for your attention.
Thank you very much. It's priceless to share the information that we generate, especially operational data in CCS projects are very rare. So I have so many questions for Ahmed, but I guess we go through the question and answer later on. The next presenter is Mr. Matt Attwood. Matt is the founder and CEO of Air Capture, a leading DAC technology and project development company currently commercializing modular and scalable DAC technology globally. Mr. Attwood has been working in the renewable energy and decarbonization sector for over 20 years, focused on DAC and CO2 utilization for the last 10 years. Prior to founding Air Capture, Mr. Attwood was the founder and CEO of Haghighi Systems, a technology company that developed the world's first carbon-negative fuel production and wastewater treatment process. Air Capture is developing several DAC pathways and integrating various downstream and commercial products such as fuels, materials, critical minerals, indoor air quality, cold chain, building materials, and sequestration. Matt, could you please be next and present your slides for us? Thank you.
Thank you. Thank you very much. My name is Matt Attwood. I'm the founder and CEO of Air Capture. At Air Capture, we are building the technology to make carbon capture commercially viable, sustainable, and locally sourced. We're trying to take CO2 out of the air, but do something useful with it. This is something that was talked about quite a bit before this morning and today. The current situation is we need to remove carbon from the atmosphere. There's a lot of discussion around what that number is, and it has to be. It could be as high as 15 gigatons per year by 2050 or larger to have a reasonable confidence interval of avoiding the threats of existential climate change. But I think what's really interesting is to evaluate the scale that's required to get to that and the time factor that's required to get to that buildup of negative emission infrastructure. What I have here is a chart derived from the IPCC AR6 report looking at confidence intervals of the scale of negative emission infrastructure capacity that would be required to avoid certain warming targets. Here shown, if we can avoid the net atmospheric carbon loading above the 2020 baseline to 839 gigatons, which requires a scale up of 1.8 gigatons per year of annual emission capacity addition. So by 2049, 1.8 gigatons, by 2050, 1.8 gigatons of new capacity coming online. That represents a 20% confidence interval of avoiding 1.5 degrees of warming. As we stand right now, without the adoption of negative emission infrastructure, we have less than a 1% confidence interval avoiding 1.5 degrees of warming. But this represents a massive economic opportunity. The Climate Policy Initiative states that we need at least 4.3 trillion of annual financial flows to avoid the worst impacts of climate change, which is an annual growth rate of over 20%. So the problem is, while we need to pull CO2 out of the air, we often forget that CO2 is an essential input to the products we consume every day. Things like carbonated beverages, food production, dry ice in the cold chain, agricultural products. So what we do is we build a modular direct air capture platform. It's quite simple. The machine is about the size of a large refrigerator. There's a fan that draws CO2 through a series of contactors. The contactors have a sorbent on them that capture the CO2. We then take that sorbent, once it's loaded and full up with CO2 in about 15 minutes from the air, we inject low temperature steam. That low temperature steam then releases the CO2 from the contactor, which we then collect and try to do something useful with it. For example, agricultural products, dry ice, beverages, and synthetic fuels. The framework for getting to speed and scale, in our view, is to develop and deploy a modular DAC system. It's a low-cost, scalable platform that's designed for scale-up manufacturing. Ultimately, we want to build these machines like cars are built today. We want to focus on the learning by doing curve. Presently, the cost of direct air capture is quite high, but by getting on the learning curve and developing the technology into near-term commercial economic applications, we can reduce that cost as we scale up the technology. And we believe that there's no reason why we can't get well below $100 per ton for direct air capture technologies. A little bit about what air capture is working on now. We are the first project, direct air capture project, funded by the US Department of Energy. And we've deployed this facility at the National Carbon Capture Center with the first testbed project there. It's a commercial design for manufacturing pilot scale program that's currently undergoing real world testing. This is a facility in Wilsonville, Alabama in the US. And you can see on the right there, our modular technology machine on the left, where we will demonstrate pure direct air capture, as well as direct air capture combined with post-combustion capture. We have a number of different projects that we're working on today, where we're looking to deploy our modular scale DAC technology into a number of different commercial markets, mostly currently today in the merchant market of CO2. The merchant market of CO2 is a very well-developed commercial market, nearly 30 billion AUM globally, where folks need to purchase CO2 for the products that they produce every day. Our current projects include direct air capture for indoor agriculture, for dry ice and cold chain, beverage carbonation. We're applying our technology to indoor air quality, to connect to buildings to reduce the CO2 that's inside the building and reduce the building's energy input. We're also working on projects where we're taking carbon neutral hydrogen developed from offshore wind with direct air capture to make aviation fuels, as well as applying our technology to make lithium carbonate from geothermal brines. A couple of projects that we're doing at scale right now. We have just recently announced a project with Carbon Built and Blocklight, where we are taking our direct air capture machines on site with Blocklight's facility. We are pulling CO2 out of the air, injecting that into the concrete plant, where they're making concrete masonry units or building blocks for the built environment, carbon negative. We also have two other scale-up projects that we're working on. One is we're taking our direct air capture process and recovering waste heat from a nutrient fertilizer facility in eastern Washington state in the US. And we're electrochemically converting that CO2 to formic acid, which is the liquid hydrogen carrier. And another project where we're scaling up, where we're taking waste heat from a nuclear power plant that's operated by Southern Company. We're taking that waste heat, we're capturing CO2 from the air, and we're injecting that in the ground for geologic sequestration. So with that, thank you very much for your time, and I look forward to answering questions later.
Thank you for your interesting presentation. The next presenter is Dr. Zeyad Ahmed. Dr. Ahmed is an environmental process engineering specialist at Saudi Aramco Environmental Protection. With 30 years of industrial and academic experience, he is currently leading the effort towards an in-situ CO2 mineralization at Saudi Aramco. Prior joining Aramco in 2014, Dr. Ahmed was a faculty member and a research professor at Michigan Tech University. He also worked as a consultant and professional engineer for multiple engineering firms around the globe. Dr. Ahmed holds a PhD and a master's degree in environmental engineering from Michigan Tech University and master's and BSc degree in civil engineering from Mosul University. His area of experience includes separation and mass transfer operation and their applications to CCS and water technologies. He's currently focused on the development and deployment of large-scale water-based CCS technologies, and I would like to invite him for the next presentation, please.
Thank you very much. Thanks. Well, it's a pleasure and honor to be here among you now. You heard Professor and presentation after lunch, I'm sure. That will add up to you staying awake for a little bit. I'll be talking about CO2 sequestration and reactor formation. My colleagues covered conventional geological sequestration, and this has been there for decades now. There's expertise there, technologies and companies, providers. In situ mineralization is relatively new. We are just starting to see in situ mineralization being implemented in industrial scale, and just right now it's being increased to a larger scale. So I'll be talking about our efforts in situ mineralization, give just a brief description of the in situ mineralization process and how it happens, and then talk about case study in Iceland, and just tell a little bit about what we are doing. So in situ mineralization is different from conventional carbon sequestration because it's chemical sequestration. It's mineralization of reactor formation. So that sparkling water that you see in front of you is acid. So when you inject this in reactor formation, which is a basic formation, you have acid-base reaction. And simply acid-base reaction, as a fifth grader would tell you, it just makes salt or secondary minerals. So it's permanently storing CO2 as a secondary mineral. It does not require pure CO2 because you can dissolve lower purity CO2 into water and inject it, so we don't actually require supercritical or high concentration CO2. And the cost can be competitive if the conditions are right. And we'll get into this in the slides. So the successful in situ mineralization requires reactivity. So the formation has to be reactive. The type of rocks that you have has to be reactive, basic mainly. And reactive by itself is not enough. You have to have injectivity. So like basalt, for example, it can be like a glass. And you cannot inject things in a block of glass. But glass can also be shattered. And then you have permeability, and then you can inject things into that glass. That shattered glass, we're talking fracture permeability, not the matrix permeability that we are all aware of. Also, another factor is the proximity to CO2 source, unless you have a good friend like Matt who can do DAC, and then you can just bring him and put him where the basalt is and it becomes perfect. So these three available in the western region of Saudi Arabia, that's what tempted us into studying these formations in the western region of Saudi Arabia and look into whether we can do this or not. The case study actually is in Carfix in Iceland. Carfix was in two phases, Carfix 1 and Carfix 2. In the first phase, it was a formation testing. So they injected CO2 along with water, and they observed with the tracer, and they observed the tracer, conducted tracer study to see how much of the CO2 stays and react in the formation. And after that, they moved to Carfix 2, in which they are injecting right now, 24,000 ton of CO2 per year and H2S. So by the way, this works for H2S as well. So if you're worried about H2S, anything that dissolves in water and makes acid could be sequestered. So what they're doing in Iceland now is they're scrubbing H2S and CO2 from the emissions of their power plant, and they're injecting the water into the formation where it reacts with basalt, and it's actually recycled. The water is recycled. The system itself has 1 million ton per year capacity, but they don't have that much CO2. So what they're doing is with climb bores, actually they're taking DAC and they're injecting the CO2 from the direct air capture also within the same system, which is the Orca plant. They're injecting about 4,000 tons per year, and I think Microsoft, they were just talking about it, they were part of this as well. Now they are into the larger scale, which is CUDA terminal, and with this they will get CO2 shipped from mainland Europe. One tanker will be going back and forth to do 500,000, 500,000 ton of CO2 per year, just one vessel. And they're hoping to expand it to 3 million tons per year by 2032. So that's large scale, kind of. There's another Seastone project that they're working on right now, and that's even a bigger scale. So here you get it, from small scale to large scale. This is from a concept into a large scale facility that will be receiving CO2 from Europe. In Saudi Arabia, the west coast of Saudi Arabia has lots of reactor formation, lots of basalt to be specific, and also ultramafics, starting from Jordan down to south of Yemen. If you've been in the area, there are lots of dark-colored rocks and mountains everywhere on the west coast. In Jazan, at the south, there's the oceanic crust, which is we call old basalt. I don't care if it's old or new, as long as it's reactive. So we are looking into this, and as you can see from the map here, there are lots of emissions as well. So you have the source of emissions, and you have the sinks at the same location, which is crucial. In Yanbu and Rabel, we did some exploratory work, and we found anorthosite and pyroxenite, and those react as well as basalt as well, and then with the acidic water. And there's the Harat, which is extrusive basalt, the volcanic flows and fresh basalt near Al-Madinah Munawwara. So there are lots of locations. Actually, just by looking at this, we looked into other locations as well, but we had enough. I said, okay, so we know that we have lots of reactor formation. Let's focus on one of them and start examining them. So we decided to go with Jazan because there are the Jazan IGCC complex, Jazan refinery, many sources there, and because we liked the Jazan formation. It actually extends from south of Jeddah to almost to the borders, or even below the borders with Yemen. Just preliminary study, we found more than 4.2 gigatons of capacity that's accessible to us immediately. And there's a Olikar AL published paper last year in the International Journal of Greenhouse Gas Control. If you would like details, you can look into this paper. Next, after we have basically first we got the outcrops that we tested, and then we start drilling. We zoomed in areas where we think that permeability could be good, and we started drilling, getting rocks, and testing them as well. And that actually confirmed our measurements, initial measurements, and that was very encouraging for us to proceed to the next phase. And then the shattered glass, that's where comes the fracture study. So there's another paper we published in the Frontier in Science, and you can see from this picture how fractured that basalt is. You pour water in this basalt and it'll just disappear immediately. So it's highly fractured. Basically, that's what all the paper says. It's highly fractured, go ahead. So it gave us the green light to go to Jazan, start drilling and logging wells. We drilled a total of 10 wells, 7 monitoring wells and 3 deep wells. First, we established the connectivity of the groundwater among these wells, and then we did a tracer study just to characterize the hydraulic flow between these two wells. And then we started to inject CO2 with tracer to close the loop and determine the capacity. And we started injection in March, and we expect to inject for 6 months. With the data that we collect, we'll be able to tell exactly how much the capacity is. So what's next? You know, this is all new science. There's no exploration methodology for basalt. We, as an oil and gas company, we know exactly how to explore for oil and gas. We have lots of experts in this field. But when it comes to exploration for reactor formations, this is new. It's new to us. We formed the team. We thought 5 people would be enough. Now we are up to 50 people. We thought 2 universities would be enough to help us. Now we are up to 12 universities, and we are establishing the methodology, actually. Because by doing this, by learning from our mistakes, by identifying the needs, what makes this work and what doesn't make it work. So by doing this, actually, we kind of developed an exploration methodology. And that's the first outcome of our effort. It's the new methodology for assessing CO2 storage potential in reactive rocks. And after you get the capacity, you have what you do with it. Then you have to model it. You have to create 3D modeling, and we did that also with the help of some universities and 3D reactive transport models. We will feed it with the data we got from the tracer study, and then we'll know exactly how much capacity. In addition to that, you know, Iceland case was the first case. So there's lots of innovation and engineering and process innovations that you can actually introduce into the technology. We have a total of 12 patents that we actually filed, and 4 of them are granted for the process. So this is our story with in-situ mineralization. We learned a lot in the last 4 years. It's a new frontier. It works. It's not a competition to conventional, by the way. They're siblings. They're not rivalries. But where you have appropriate formation for conventional sequestration, be it, but in many other areas, you don't have that. And there are lots of basalt. There are offshore basalt, there's onshore basalt, there's lots of good formations. Just have to go out there and look into them. And if there's a close source, be it, that's excellent. If not, there are other potential for like blue hydrogen facility, where having the reactor formation would be the determining factor for where the new blue hydrogen facility would be, right underneath you. So that's where you build the new hydrogen facilities or direct air capture. With that, I thank you, and I think we'll be answering questions after the following presentation. Thank you very much.
The last but not least is Mrs. Elham Kolahchian. Before I introduce Elham, let me give you an interesting fact. 22 years ago, Elham and I, we did our undergraduate degree at the same university. And we went our own way. We went to different countries, we studied, we worked, and now we live in different countries. What's the chance of meeting each other in a CCUS conference in Qatar? And on top of this is the first time for both of us to be in Qatar. So it's a small world, it's a small business. I think the more we share, the more we work together, I think we all gain from that collaboration. So Elham leads 4401 subsurface team. Elham has over a decade of international experience in reservoir characterization and well construction. At 4401, she manages design and execution of subsurface structure, as well as developing monitoring and verification plans for mineralization processes. Elham, can I ask you please to present your slides for everyone? Thank you.
It's a long way. Sorry. Assalamu alaikum and good afternoon, everyone. And thanks for the introductions, Hooman. And thanks to Dr. Ahmed for making my job easy and explaining what mineralization is and how it works. I start by introducing the company. Oh, went too fast. 4401 is a carbon removal startup company. We're based out of Oman. And we are developing a technology to safely and permanently remove carbon dioxide by in situ mineralization into peridotite rock formations. So peridotite is another kind of the igneous rocks. It's ultramafic. It has unparalleled mineralization capacity. And it's normally found in the mantle of the earth, but luckily in many parts around the world, it outcrops to surface, and it makes it a perfect carbon sink. It's found in Oman, in UAE, North America, parts of South America, parts of Europe, and all the way to Australia and Japan. So in Oman, we have the biggest and best accessed massif of peridotite in the world. The capacity is up to 50 trillion tons of CO2 to be mineralized into basically Oman rocks alone. And this is just to put it in perspective, is like all the emissions that humankind has ever put in air. So the capacity is there, potential is there. And if you see this picture, and if you've ever been to Oman, you know, hiking on our beautiful mountains, you come across this signature rock with the white veins, and these are surface peridotite. It's found, you know, on the mountains all over Oman, and again, parts of the world that I mentioned. And when these rocks are in contact with water from rain, you know, the water in the wadi, and the CO2 from the air, they mineralize into these white carbonate rocks inside the existing fractures of peridotite. And our founders were basically inspired by this natural process and founded the company in Oman about 3 years ago. And what we do is we accelerate this natural process. We accelerate it by hundreds of folds to make it, you know, viable for carbon removal. How do we do that? It's just in this simple diagram, starting from top of the cycle with sourcing the CO2, either from DAC or point source. We take the CO2, dissolve it into water, and drill injection boreholes into peridotite to access the rocks to certain safe depths, and inject the CO2 down into the subsurface, accessing the rocks where they mineralize rapidly inside the existing fracture network. Within a year, the CO2 is gone, converted completely into rocks. We power our process with renewable energy, and we also drill observation boreholes for monitoring, you know, and verification processes. This shows an overview of our current projects in the region, in the Middle East. We have our headquarters in Oman, as well as UAE. We started our company with a small pilot project in Oman, where we successfully proved that the technology works. Mineralization happens in peridotite, it happens rapidly, but most importantly, it happens safely. Then we started the demonstration project in UAE. This one is in partnership with ADNOC, Masdar, and FNRC, where we're showcasing our technologies basically in peridotite in UAE. And then we have our large-scale demonstration project in Oman, in the Hajar Mountains, and that's where we're going to start commercial injections by next year. We also have our innovation hub, where we do most of our research and development, and our goal and plan is to scale up to the point that we can have major contribution into global goals, you know, to remove billion tons of CO2 by 2050. And that's what I have for today, and I welcome all the questions. Yeah, thank you.
Elham, thank you very much. Okay, so if you have questions, please post it in there because I can see everything. So we can hopefully answer some of the questions. But I have one question for myself I would like to start with, and that's basically for Ahmed, if you don't mind. Ahmed, Equinor is one of those companies that has significant experience in design, in energy industry, in CO2 industry, and also in operation of CCS projects as you presented. And I know you support so many different research and development activities, and I'm really interested to know if you do work, for example, in Norway, how do you make sure that that knowledge is passed on to your other colleagues in the rest of the world? And also you mentioned that you share some of the design and operational data live on the website, on your website, or maybe Norwegian government website, to be accessible for others. So you're basically trying to share your knowledge. I would really like to know how has been the process for you? How do you make sure that the work that you deliver in different parts of the world is using the experience of your projects executed and designed in different locations based on their demands, if that's okay?
Thank you, Hooman, for the question. And in Equinor, we're a believer that knowledge sharing is key in order to create any industry. Equinor started in Norway 50 years ago, very, very small company, learning from, at that time, the American companies working in the North Sea. And without that knowledge transfer that happened between these companies and Equinor, we wouldn't have been in the place we are in today.
Yes.
So it is truly something in our DNA that we need to share the knowledge that we're gaining, especially in areas like CCS or renewables in general, which are new industries. And in order to scale these industries, the collaboration, and in the previous sessions, the word collaboration has been repeated probably 20 or 30 times. And I cannot stress on how important that is. Collaboration really is key between operators like us, service companies, the government, the research institutions. Mm-hmm. Without that collaboration, any of these solutions for the energy transitions are not going to be materialized. So the example that I shared, for example, the Sleipner carbon capture and storage project, we believe that it's the right for the public to know if this project is going to be impacting them or not. Part of our sustainability, part of our social responsibility is to share any information we're receiving to make sure that the public is confident and comfortable that this CCS project is not going to be impacting their water, their land. So again, in our opinion, the more you share, the more you gain.
Absolutely right. Thank you very much. That was perfect. Maybe for the next question, I go to Matt, if you don't mind. Matt, you talked about DAC, and I know there are some challenges associated with the technology. Can I ask you to elaborate on DAC sequestration mainly? And maybe if you can compare it against point source. Like, for example, if you can capture CO2 and whether it's going to be easier, more efficient, cost effectively from cost point of view and maybe from energy efficiency point of view, if you don't mind.
Sure, I'm happy to. Point source capture of CO2 is always going to be lower cost than direct air capture. One of the challenges of point source capture is that it increases the overnight cost of power to the power plant that the post-combustion CCS project is attached to due to the chilling load that's required from the heat that's produced when the CO2 is captured. That high concentration of CO2, however, is much more capital efficient from a capture standpoint. On the other hand, that's not enough. We must pull CO2 out of the air and sequester it. So one of the things that we look at is ways to leverage combining direct air capture with post-combustion capture together. For example, we can capture CO2 out of the air with our machine, 100 tons per year per machine, and capture 100 tons of post-combustion capture in the same machine. One unit does 200 tons, and then sequester that. The energy cost of DAC is fundamentally different than post-combustion capture. Post-combustion capture requires cooling the system, cooling the CO2, whereas direct air capture requires heating up the system in order to release the CO2 from the sorbent. Direct air capture, especially low temperature direct air capture, like the processes that we utilize, can be seen as to replace the cooling towers, for example, in thermal power generation. So you could remove the cooling tower, put in DAC. The DAC can then take that low temperature steam, saturated steam, condense it, pull off the CO2, and then provide that condensate back to the power plant. This can be more capital efficient. It can be energy efficient from a heat source. But the first rule of direct air capture is you have to move a lot of air. There's no way to get around that. So we must pay the power demand of that one way or the other. Beyond that, it's all the same, because we just have to make liquid CO2 and inject it into the ground.
Perfect answer. Thank you. Thank you very much. For the next question, I'm going to go to Zeyad, if that's okay. What you presented is extremely interesting, and I can see so much opportunities in the approach that you took. Can I please ask you to elaborate a little bit more on the challenges in order to scale up the work that you proposed? Is it something that is mainly applicable for certain regions or certain countries, or you think this could have an opportunity in the rest of the world as well? I think you indirectly answered that during your presentation, but I would really appreciate if you can elaborate a little bit.
Okay, thank you. A great question. Well, there's many, many ways to ruin this, especially if you don't approach it the right way for mineralization. You could go to the wrong place with the wrong approach, and then the results, if it's not studied well, the results will be negative, not promising. So I would say the main challenge is the human capital, the knowledge, because this is new, and people are just looking into it now. There's no exploration methodology that you can follow into determining what formation is good and what formation is not good. I worked a lot in the lab. Things work in the lab, but when you take them to the field, they don't work for a reason or another. So there is a progression that has to happen for this to work, and that's precisely what we are doing, and that's the topic of this session, actually, from how to go from lab to field to large scale. And the challenge is that these formations are not identified, are not quantified, and the capacities are not determined because this is new. Nobody was interested before in this. It's not like oil and gas, I said. People know a lot about it and they know how to explore it. So it's important to consider the high potential formations and areas, and then take through the progression from laboratory testing, formation testing, demonstration facility, and then large-scale deployment. Same as they did in Iceland, same as what we are trying to do right now. And it's case-specific. You know, it's every spot is different. You know, a new thing by itself. You know, every formation has different characters, and there's no pure mineral in one formation. You know, there's a whole matrix of minerals in every formation, and hundreds of reaction pathways. The products, the temperature will affect where the reaction pathway go and what type of precipitations you will get. The other challenge is perception. I mean, working in a country with limited water resources like Saudi Arabia, first question I get, what about the water? This is water-intensive process. Well, yeah, water is the carrier and the medium, but we don't consume water by this process. We recycle water. We are creating water on a molecular level with the mineralization reaction. So we don't consume water. As long as there's water there, we can recycle it, load it with CO2. It goes down, it reacts, makes the minerals. I get the same water again, put CO2 with it, and then it goes on and on. So it's a perception. It's the fear from the unknown. But then I think within the effort that's done in Oman is amazing. When we start seeing the results of this, when we start seeing the results of Jazan, people will feel confident that, okay, this works. And it has been working in Iceland, but then second and third confirmation, and then we will be able to apply it in large scale. Now, we had to do it ourselves as Aramco. We had to do it ourselves because there is no service provider can come to us and say, hey, I'll take your money and do it for you. No. This doesn't exist in the industry now.
That makes a lot of sense. Thank you.
Thank you.
Thank you very much. Maybe for the next one, I go to Elham. Elham, before I ask my question, I'm sure so many people in the audience might be interested to know why 4401. What does it mean?
Yes, we come up with a smart name, in the startup world. So this is the molecular mass of carbon dioxide. Yeah.
That
I think
makes
it's
sense.
catchy. Yeah.
Thank you very
Easy
much.
question. What's your next?
So let's go for a difficult one. So I would think, as a startup company, your journey and experience of starting with a new idea, a new technology, would have been very different compared to scenarios where potentially you could have the backup from a large energy company or finance supporter. I would really like you to elaborate and just say what has been your experience as a startup company, where you are, how do you think what you are proposing here can be scaled up, how long would it take, what are the plans?
Yeah, excellent question. I think, again, Dr. Ahmed explained the general challenges that we're facing in the mineralization world. I would say for a startup, we have a set of challenges that it's very common in the startup world, resources, fundraising, people, skill sets,
yes.
equipment. I would say, though, we're very lucky in the region that we are. Our main resource is peridotite. We have an abundance of it in the region. And globally, many parts of the world. So same for the renewable energy, the skill set, a lot of it is transferable from oil and gas industry, energy companies, and a lot of it is like this focused skills that has existed in the last few decades in the research that has been done in the field of mineralization in peridotite. I would say, yeah, the challenge, part of it is, and there was discussions before that other parts of the world are probably more, I wouldn't say advanced, but they're ahead of us in terms of frameworks, policy, regulations, and it would be good if we, can learn the best from them and accelerate, putting these frameworks into the specifically for mineralization, I'm sure there is a lot of focus in CCUS in general, but having the mineralization as well, included in all of that, so that would be great. I think the second part of your question was regarding the future.
Oh, the future, yes, please.
Yeah, for a startup. So I mentioned basically what we've done in the last 3 years. I would say next is for us to develop our technology further, expand in the region, but also go international. There is global potential. There is so much potential in many parts of the world. And what we eventually want to do at 4401 is to have mineralization hubs where we can partner, with DAC companies as well as hard-to-abate industries, and just have like multiple hubs around the world that could really help, with the scale up and making an impactful contribution.
Absolutely. Thank you, Elham. Thank you. That makes a lot of sense. I think we still have 7 more minutes if Amal give me the green light. Yes, I think we have 7 minutes. So maybe we can go for one more round of questions, but I'm not really sure if people in the audience, they also have any question that they would like to ask directly. I'm not really sure if the live question system is actually working or not. I received a few questions that I asked, but nothing else has came through. If you don't have any questions, I ask my question. So please feel free to ask questions if there is anything. Please, could you please introduce yourself first?
The good doctor mentioned that it's not a competition between, say, saline aquifers and mineralization. Is there a play around the difference of cost of sequestration in, say, depleted wells or saline aquifers versus mineralization? Difference in monitoring costs that might come to play with mineralization versus conventional sequestration that you're looking to lever? Or is it really just around the location of the resource and trying to pair up that the geological asset with the point source emission?
Yeah, thank you.
Yeah, so that's part of the challenge also, that data is not very abundant when it's come to mineralization. There's only a few projects that you can refer to. But the published cost of the process in Iceland is $25 per ton. $20 of it is for the capture, which is scrubbing. That's what they use. And for the engineers here, that scrubbing is not the most efficient. There are many other processes that's more efficient. So you could probably reduce this as well. However, I have to warn, carb fix is an ideal situation. So the $25 in Iceland doesn't mean that you can do it everywhere, $25 or even $50. So it's case specific. And then at some points, the saline aquifer could be more cost effective. but very often, you don't have the two options in the same location. So sometimes what you have forces you to go through to one direction than the other one. Like in Saudi Arabia, you have the sedimentary formations in the east coast, but it's thousands of kilometers from Jazan. And you don't need to transport this all the way to Jubail hub. It has to be something localized. I think that the threshold was 300 kilometers or about that. If it's more than that, don't think about it. Although the world is heading toward shipping CO2 containers in the sea, and it's becoming reality, and as the demand gets more and more and more, things that we think not feasible now could be feasible in the future.
I'll add a small point. Oh, well, this one works. I'll just add a point about the monitoring that you mentioned. So with mineralization, because the CO2 will be converted into rock and removed completely within a year in our case, there is no need of long-term monitoring and verification. So that is one thing that definitely has a lot of cost benefits, as well as just, the permanence that it's not reversible, there is no risk of basically the CO2 being released. So we monitor it as long as then we get to the point that it's fully mineralized, then that's it. Saline aquifers that they have to monitor, I don't know, it's debatable for how long, but yeah, basically forever.
Good answer. Thank you. Does anybody else has any question?
Hi, yeah, my name's Carl Street from Baker Hughes. I was just wondering if they considered combining low enthalpy geothermal with this CCUS mineralization. As you're pumping and circulating water through, well, especially on the west coast of Saudi, but maybe fairly high heat flow rocks, maybe you can combine the two.
Yeah, I can go for it. Oh, mine does.
Yeah, actually, that's where it started from. So the power plant in Iceland is a geothermal power plant. CO2 emissions come from the water that they extract from formation and H2S as well. That's the ideal case. If you have geothermal power plant, then you can use the water, whether you get CO2 and H2S from the formation or not, you will get anyways. But you can add to it. You can add to it and use this infrastructure that you already built for geothermal power harvesting for CO2 sequestration as well. Yeah, that could bring the cost down significantly. Yeah.
Fantastic. I think we have 1 more minute to go. I think it would be unfair for me to ask another question. I don't think we would have time to answer it. I just want to thank you all for listening to us and your attention. If you have any question, please feel free to find us. I'm sure we would be more than happy to provide more information. And if not, enjoy the rest of the event. Thank you.